Let's get started. Number one, the force between two bodies having identical electric charges is what? You have two negatives or two positives. Which way is the force going to go? Go this way. Right. This way we represent repulsion. Force of repulsion between the two. Number two. Let's go ahead and put that one right there. Atoms having equal or nearly equal electronegativities are expected to form what? If you have two atoms, let's just use a real world example. Let's say we have two hydrogens. Okay. Not no bonds. I mean, we've got an example right here of bonds. It's not polar. If they're exact the same electronegativities, then it has to be a nonpolar covalent bond. That would be C. That's almost a definition. Oh, this is not a good board today. Should have put some WD-40 on it before we got started. For the elements cesium, fluorine, and chlorine. Cesium, fluorine, and chlorine. Let's see. The order of increasing electronegativity. So what direction does electronegativity increase on the periodic table? Right. Lower left, upper right. Increasing electronegativity. So the most electronegative, if we're going from increasing left to right, fluorine would be the greatest. And the least would be cesium. It's in the lower left-hand corner. Oops. That'll never do. That means chlorine has to be in the middle. Okay. That'd be B. Okay. Like this. Well, I might have to use a new marker just to be dark enough against that background. How about 4? That. The electron pair in a carbon-fluorine bond could be considered. Carbon-fluorine bond. Let's see what our choices are. Closer to carbon, closer to fluorine. Okay. So we need to look at the difference in electronegativities. Which way is the dipole moment for these two? They have to be toward fluorine because it's the most electronegative. So the electron pair is going to be closer to fluorine, which would be B. Yeah, because fluorine has a higher electronegativity than carbon. Right? 5. Which of the following molecules has no dipole moment? Now, notice we're not talking about the bonds. We're talking about the molecules. Which of the molecules has no dipole? You have to know something about the bonds, and you have to know the geometry. So carbon dioxide, what are our choices? Ammonia. We've drawn all of these before. All and none. All right, we know what carbon dioxide looks like. All right, we've drawn the Lewis dot structure for that one. Right, you may have polar bonds this way, but they cancel each other out. So this one's non-polar. Ammonia, like this. with a hydrogen in the back. There's your triangular base, that. So its overall dipole moment's like that. Water is a bent molecule, like this. With two lone pairs here, like that. The bonds are polar this way and that way. Molecules overall polar that way. So, which of the following has no dipole moment? That one right there. Carbon dioxide. Now, if you don't remember the Lewis dot structure for these molecules, it'll take you a little longer because you'll have to draw the structure in order to tell which one is which way the dipole moment's going. All right, number 6. Which of the following has the smallest radius? Okay. Looking for a radius. See, what are our choices? Okay. We have, looks like all our ions except the last one. There's argon, sulfur ion, rubidium, chlorine, and potassium. Okay, if we were to look at these as elementals, we know the trend for the elements in the periodic table. Atomic radius should decrease from left to right, right, and increase from top to bottom. So it should decrease from lower left to upper right. Atomic radius. Right, so if we looked at them that way, the smallest radius would be the one furthest up in the furthest upper right-hand corner, which in this case would be chlorine. Except chlorine's got an extra electron, which makes it go like that. And that extra electron would go in and make it look like argon. All right, so what we have to do now is say, okay, what happens when you lose an electron? And where does the electron come from? Okay, so potassium is over here, and argon is up here. And so potassium's in the 4th period, argon's in the 3rd period. Chlorine is also here, up there, and sulfur's right here. Right. So that sulfur's bigger than chlorine, and chlorine's bigger than argon, and especially since they've got extra electrons with them. What happens to potassium? Well, potassium should be a little bit larger as not the ion, but the neutral atom. And that's simply because we're moving from this level to this level. But once you take away that electron, and potassium has one more proton than argon, then that should shrink it below argon's level. So potassium should be smaller than argon, right? And chlorine and sulfur ions would be bigger than argon. So far we've got potassium as the smallest. Now what about, we haven't looked at rubidium yet. Where's rubidium? Rubidium is down here. So it's going to be bigger than potassium, even though it is an ion, because it has another energy level and 18 more protons. That makes this one bigger than that one. So potassium looks like it's going to be the smallest one. This is a difficult problem. I'll grant you that. Because we're not talking about neutral atoms anymore. We're talking about ions. What happens to the ion when you add electrons to its size? Add electrons or take electrons away. Some of these things are easier to explain than others. About 7. Which of the following arrangements is in order of decreasing size? Okay, now we got a real problem. Okay, what do we have to choose from? Gallium. You know what? What if we do this? Try to put them in the periodic table in relative position. How about that? Gallium 3 plus. Let's see, we've got I'm gonna make this is 2, 3, 4, 5. There we go. So gallium is in the 4th. It's right here. 3 plus. Then calcium is over here. 2 plus. I'm just looking what unique ones we have. Then potassium is right here at 1 plus. And chlorine is over here in the 3rd period, right there. And sulfur is right next to it. Right? And then sulfur, chlorine, potassium, calcium, gallium, potassium. Is that all the unique ones we have? It looks like it is. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, now we got to arrange these in decreasing size. All right. If we look at the neutral atoms, the 4th should be bigger than the 3rd. Except that now we have added electrons here with not an increase in protons, which makes these guys really balloon big. So I would say these would probably be the biggest. Let's see, in decreasing size. So I would say since sulfur has 1 less proton, 1 fewer proton than chlorine, then 2 extra electrons are going to make it huge. Yeah, that size, like that. Now that you've got more, you've got another level with more protons in it, then they generally, the neutral atoms get smaller from left to right, then I would think gallium would be next. Oh, excuse me. No, we're losing 3. It's getting smaller from this size. No, getting smaller left to right. And then we're losing 3 electrons. So this one would be the smallest. Yeah. Gallium, the 3 plus, would be the smallest. Then calcium, 2 plus, and then potassium. That's what I think it should be. And if I'm right, that should be B. Yep. That's making certain assumptions, right? The only way to be absolutely sure is to get the data, right? And work from hard numbers. In the reaction between magnesium and sulfur, the magnesium atoms, what? Oh, we're going to go magnesium plus sulfur. And it's going to yield something. What usually happens? Usually the metal likes to lose electrons. So we transfer electrons over here. That is, magnesium is going to become a 2 plus and sulfur is going to become a 2 minus because of where they are in the periodic table. Magnesium is an alkaline earth. They nearly always make 2+ ions. Sulfur is a chalcogen, and they nearly always make 2- ions. So in the reaction, the magnesium atoms become anions. No, cations, excuse me, cations. This is a cation. This is an anion. Right, so that answer would be B, become cations. They don't form polyatomic ions and they don't share electrons. The reason they don't share electrons is that sulfur has a much, much higher electronegativity than magnesium. All right. Number 9. Choose the molecule with the strongest bond. Okay, out of the choices we have here, A, B, C, D, and E is an oddball. What does it say? It says all are equal. Okay, so we're working our way down. The diatomics. I think I got those in the right order. What we find is that the strongest bonds are going to be formed where the electronegativities are larger and you can get the nuclei close together. So if you start with iodine, those atoms are huge, right? And their valence electrons are more diffuse. Right? So you can't get them very close. That doesn't give you as stable a situation as bromine. So from iodine to bromine to chlorine, I know that we're increasing electronegativity and decreasing the size of the atoms so they can get closer together. So the bond strength should be this trend, like that. Okay, here's the problem. Here's the quirk in all this. Fluorine is very electronegative, right? So, and it's the smallest atom. So it should be able to get close. The problem is when you get that close, when you get the nuclei that close, the protons start pushing it away from each other. So the bond strength here goes back down. And this one is the strongest bond, the chlorine. Dichlorine is the strongest bond because the fluorine atoms get too close to one another in their bond. It weakens the strength of the bond. And if we had numbers to go with it, we could prove it. All right. Let's see who's next. Number 12. These molecules have a 0 net dipole moment. Oh, we're looking at the ones just above. Okay. Lewis, okay, we got 4 of them. All right. Four, 5. We have 5. Okay, so here, 2, SF6, O3, that's ozone. PCl5, 5. Okay. So in order to determine the dipole moment here for any of these molecules, we have to know their structure. We drew this one in class, right? That. This is a trigonal planar. Right? Each of these bonds is equivalent, pointing to an isosceles triangle. Their dipole moments cancel out. So this one is nonpolar. Okay. has a zero net dipole moment. NO2, we might have to draw this one. So valence electrons for nitrogen, that's 5 plus 2 times 6 is 12 is 17. Okay, so we draw the N, we put the O and O, so that's 2, 4. It's 13 left over. 2, 4, 6, 8, 10, 12. We have to put the other one right there. Okay. So what does that do? Well, we've got 1, 2, 3. All right, 3 is trigonal planar. So we're going to have a nitrogen here, oxygen's there. Oh, excuse me. I'm not finished, right? I'm getting ahead of myself. That's not an octet. So how do you get an octet out of that? Well, we take these two and make a bond. That's 2, 4, 6, 7. If we try to make another one, that'd make nitrogen 9. So we have two choices. We can either put a double bond here and nitrogen would exceed the octet, which it can't do. Right? No, it cannot exceed the octet because nitrogen doesn't have access to d orbitals. So we're stuck there. This is going to be trigonal planar. That. And oxygen is more electronegative, this direction. And with that lone electron up there, you get a little bit of dipole moment that way, but these two outweigh that one. So I suspect its dipole moment is like that. It's definitely not nonpolar. I can say that much for sure. All right, so 2 doesn't work. How about SF6? Well, let's see, sulfur has 6 electrons, fluorine has 7 times 6, 42, is 48 valence electrons. So now we have sulfur, we have 1, 2, 3, 4, 5, 6 fluorines. Okay, 2, 4, 6, 8, 10, 12. 12, so that's 36. 2, 4, 6. If we put 6 electrons around these fluorines, 6 times 6 uses up all the, right? Just put 6 around each one. That means each fluorine has its octet. And sulfur exceeds. So these 6 fluorines go into an octahedral with equal positions everywhere around it, so they cancel one another out. This one is nonpolar. So we got 2 nonpolar so far, this one and this one. How about ozone? Let's see, 3 times 6 is 18. So we don't have to worry about which one's in the center, right? Just take your pick. 2, 4 equals 14. 2, 4, 6, 8, 10, 12, 14. That. Then we need to make an octet. So how do we do that? Well, we have to use pairs from the outside. We can't use that one because that one won't help us any. So if we move these 2 over, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. There we go. All right. So, well, you know what? I'm thinking, well, the temptation is to say, since oxygen to oxygen and oxygen to oxygen, we don't have polar bonds. But here's the rub. You may not have polar bonds, but you do have lone pair electrons. Right? So if you count, what is the geometry around that central atom? 1, 2, 3. So you have the central atom, you have an oxygen over here, you have one over there, and you have a lone pair up here. So this is one of those cases we didn't cover in class, where you have nonpolar bonds, but a lone pair, which gives you a dipole moment that direction, right? Because you've got that extra electron pair up here, right? Which gives it a a negative character on this side of the molecule. So this one is definitely polar. And we already saw this one was polar. How about PCl5? Well, let's see, phosphorus is 5 valence electrons, and 5 times 7 is 35. So we have 40 valence electrons. Right? So we put a phosphorus here. 1, 2, 3, 4, 5 with chlorines. 2, 4, 6, 8, 10. We got 30 left over. 2, 4, 6. If we put 6 around each one of these, that gives them octets, and 5 times 6 is 30. So we've used them all up. Now, what's the geometry here? A trigonal bipyramid. And that means all chlorines are spaced in just the right position to cancel out any dipole moments from the bonds. So overall, this one is also nonpolar. So we got 3 of them. 1, 3, and 5 are nonpolar. And that would be B. All right. Did I lose anybody? I'm moving a little fast, probably. This is probably the trickiest one right here, because the bonds technically are nonpolar, but the molecule is polar. It's one of those exceptions, right? I probably said something like during the lecture, you have to have polar bonds first, and then you have to look at the geometry. But in this case, you got nonpolar bonds, but the molecule is polar because of that lone pair. All right, number 13. Let me see how many I marked off. So once we get halfway, seems like it'd be fair. Let's see, that's 5. And 9, 10, 11. I got a mark here. That must mean we get up to 28. That should be halfway. Yep. We could go a little further, but definitely once we get 28 under our belts, then we're in the neighborhood of stopping. How many electrons must be shown as bonding or non-bonding electrons in the Lewis structure, whose skeleton is this? This is an organic compound, but we don't care, because we're given all of the elements in there, and all we have to do is add them up. So how many hydrogens do we have? 1, 2, 3, 4, 5, 6. So that's 6 electrons, right? 6 valence electrons. 1, 2, 3, 4 carbons, right? That would be 4 times 4 would be 16 electrons. And we got 1 oxygen, right? So that 1 oxygen is 6 electrons. Right, so 12, and it'd be 28. 28 electrons have to be shown in that skeleton. Okay. That's it. That's how simple that problem is. Just add up the electrons, the valence electrons. Let's see. 16. In the Lewis structure for ICL2 minus. Okay. How many lone pairs of electrons are around the central iodine atom? All right, so we've got 1, 2, 3 halogens. 3 times 7 is 21, plus 1 for the charge. So we have 22 electrons that have to be placed. Iodine's going to be in the middle. We have chlorines. I'm sorry? Oh, halogens. Yeah, they have 7 valence electrons. Sorry. 3 times 7 equals 21 plus 1 for the charge. There we go. Okay. All right. So there's our beginning structure. So we've used 4 of them. That's 18 electrons left. Okay, 2, 4, 6, 8, 10, 12 gives you octets here and here. So that's minus 12 more. That's 6 electrons. So we have to put the 6 electrons, put 2 here. Right? That's 2, 4, 6, 2 more. Now iodine's got an octet, but we've only used up 4. So we have to put 2 more. Okay. That means iodine is going to exceed the octet. And to answer the question, how many lone pairs are around the iodine? 3. 3 lone pairs. Now, what would be the electronic structure for that? 1, 2, 3, 1, 2, 3, 4, 5. That would be a trigonal bipyramid. You would have like this, and up like that, down like that. Iodine in the middle. Where would the lone pairs go? They would go here, 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 and here. And then you have the chlorine here and the chlorine here. So this molecule is linear and nonpolar. Even though chlorine is more polar than the iodine, the dipoles cancel one another out. I mean, that's not part of the problem, but I thought I'd throw that one in for free. All right, 16, 19. How many resonance structures can be drawn for the molecule O3? I should have left that one up there. Ozone. All right. See, can I remember how the ozone went? Like that. Like that. Like that. That 2, 4, 6, 8, 10, 12, 14, 16, 18. 3 times 6 is 18. So I got all my electrons in there. So how many resonance structures can we draw from this? Well, we formed one structure by moving a pair over here into that bond. Well, we could do it from the other side instead. Now we have like that, that. So only 2 resonance structures can be drawn for ozone. Okay. Uh, 20. Okay. Which of the following types of molecules always has a dipole moment? A, B, C, D, E. First type, linear molecule with 2 identical bonds. Linear molecules with 2 identical bonds. Okay, that can be a little confusing. A linear molecule could be just 2 atoms. But if you have 2 identical bonds, I think they're saying that you have like this, those bonds are identical. Always has a dipole. That one will not have a dipole. Because these bonds are identical. They may be facing the other direction, out or in, they cancel themselves out. So this one is nonpolar. How about B? Tetrahedral molecule with 4 identical bonds, equally spaced. That's definitely nonpolar. Any example will do. Methane. Identical bonds all around. That's nonpolar. So it never has a dipole moment. How about trigonal pyramid molecule, 3 identical bonds? A trigonal pyramid. How do we get a trigonal pyramid out of a molecular structure? I work from examples. The example I think of as a trigonal pyramid is ammonia. Okay. There's your trigonal bottom, and there's your lone pair. This would normally be an electronic tetrahedron. But when you cover up that, the molecular structure is a trigonal-based pyramid. And this one would always have a dipole moment. Even if the bonds were nonpolar, you'd still have this lone pair up there. And that would always give you a dipole moment. This is polar, always. Oh, we found our answer. Trigonal planars with identical bonds, they're never polar. And the last one, none has a dipole moment. Well, that's wrong. Okay, so we found the one. The understanding here is that the only way you can get a trigonal pyramid is to have these 3 to form the base of the pyramid, and then a lone pair up here. You always have to have that lone pair. Otherwise, you can't get a trigonal pyramid out of this, out of any other structure. 21. Right. Which set contains the atoms listed in order of increasing electronegativity? Increasing electronegativity. All right. You know, I like that using the periodic table. So we have 2, 3, 4, 6. Where are they? Fluorine is way over here. Right. Nitrogen is over here. Is oxygen in there? Yeah, oxygen's there. Oxygen's there. Carbon's right here. And let's see, silicon. Silicon is below carbon in 3. Yep. So phosphorus. Phosphorus is below nitrogen. Nitrogen, oxygen, fluorine, oxygen, chlorine. Chlorine is here. Is sulfur in? Yeah, sulfur's in there. All right. Nitrogen, oxygen, chlorine, fluorine, silicon. Okay, I think we got all of them. 1, 2, 3, 4, 5, 6, 7, 8. 5, 6. Yeah, I don't see any new ones. Okay, if we're looking at increasing electronegativity, right? The most electronegative is going to be fluorine. No doubt about that. The least electronegative should be silicon because it's down to the left. So if the test taking technique, right? If you've got a multiple choice test and you're in a hurry, then look at both ends and see if we can eliminate a bunch, right? We've got B, C, and D, right? B, C, and D are possible, right? Because fluorine is on the far right. On the far left is silicon. All right, so silicon, let's see. It could be D, possible. C, N-O, Cl's below. All right, so this one can't be it. Right, it's out of order. So B could be it if we include phosphorus, nitrogen, oxygen, fluorine. That's the right order. Right, increase, increase, increase. Right, so this one would be, right, this would have nitrogen would be in here somewhere. Right, so B seems to be the best one. We were able to eliminate A and E, and then we go at the other three. Okay. Still processing? No? Okay. I haven't used this approach before, where I actually, laid out the periodic table like that. I think I like it that way. I think I'll use that from now on. 22. Which choice has the bonds listed in order of increasing bond energy? What do we mean by bond energy? We mean how much energy does it take to break the bond? All right, so how much? Oh, what in the world? I think Spring has sprung a leak. Increasing bond energy. All right. B, C, D, E. Okay. HF, HCl, HBr. Actually, the strength of the bond for A should be the other way around. HF should be the strongest, Cl and HBr. That earlier question where we had the diatomics, right? If this were chlorine here, this would be the strongest bond. But now we're looking at each one of these with hydrogen instead. And hydrogen only has one proton. So you can get really close with this one without having a problem. So HF is the strongest, then HCl, then HBr. So A is backwards. So A as given is wrong. If we have a carbon bond is less than a double bond, is less than a triple bond, that one's a good choice, right? So test taking technique, all of these can't be. C should actually be chlorine is the strongest, then fluorine, then bromine, right? So that one's wrong. And then N2 less than carbon-carbon bond. What? Oh, okay. No. What is N2? It's got a triple bond in it. Right, so it can't be less. So D has to be wrong because they put this one at the shallow end. And the other bonds, the carbon-carbon bond for this one, C2H4, that would be a double bond. So this would be greater than that one. And this would be greater than this one. And these all have hydrogens on them. I didn't draw in the hydrogens, but that's what they are. All right, so that one's turned around backwards. So the only one that makes sense is this one right here. 23. we're getting there. Yeah, we're in good shape. Might want to go a little farther than 28 so that it'll give us more time on Tuesday to talk about the lab. In the gaseous phase, which of the following diatomic molecules would be the most polar? The most. Gas phase. Okay. Well, and that's important, gas phase, because at room temperature, cesium fluoride would be a solid. Right? That's an ionic compound. But when you move it into the gas phase, now you got individual cesiums connected to fluorines. So that would be the most polar bond in there because cesium and fluorine are at opposite ends of the periodic table. Right? That one's easy. What cesium is like 0.7, I think, and fluorine's 4. So that's 3.3 difference in electronegativity, which is huge. All right, 25. Which of the following ionic compounds has the largest lattice energy? Lattice energy most favorable to a stable lattice. All right. Largest lattice energy. Okay, here's the way you approach this one. Lattice energy. Remember how we determine the lattice energy. We have the metal with its charge, and I'm just picking a charge there. This is more important. It has to be a gas. Plus the nonmetal with its charge, and it forms a solid. Okay. Now, the differences you can have when you determine the lattice energy, and this is going to be very negative. Delta H is going to be very negative. That is, it's extremely exothermic. But the thing that stabilizes the lattice are two things. How close can the ions get to each other? And what's their relative charge difference? So 2 plus would be greater than 1 plus. And 3 plus would be, as far as charge goes, 3 plus for one and 3 plus for the other one, or a 3 minus for the other one. Or if you had the greater the charge difference, let's say it that way. The charge difference must be large. Okay. And then the distance, spacing, small. So let's see which one has largest charge. Barium. Let's see, where's barium? The barium. Barium is 2 plus. Let's just put them in order. A, B, C, D, and E. Gotta make more sense. We got barium oxide, beryllium oxide, cesium iodide, sodium bromide, and barium sulfide. Okay. So what are the charges here? Well, this is an alkaline earth. This is a chalcogen. So there's our charges. Beryllium is also a 2 plus and a 2 minus here. Cesium is only a 1 plus, and iodine's a 1 minus. That's a plus and a minus. And barium again is 2 plus and 2 minus. Okay. So if we eliminate based upon charge first, then these have too small charge right here to be the strongest, to be the highest, the most negative lattice energy. So we've got the 2 plus, 2 minus, we've got the charges here. Now, which ones are the smallest ions? right? Sulfur is bigger than oxygen, right? So that lets this one out. So it's a between these two. Beryllium and barium. Barium is a huge atom. Beryllium is a small atom. So it's going to get closer to oxygen than barium is. I think it's beryllium oxide. Should have the highest lattice energy, the greatest lattice energy. That's kind of misleading because the greatest lattice energy is how much energy do you get back? Which one is the most negative? It gave up? Looks like it did. Okay. 26. The first electron affinity value for oxygen is blank, and the second electron affinity value is blank. Unfavorable versus favorable. Okay. For oxygen, electron affinity. Remember when we have oxygen gas, and we're going to see how does it attract an electron, and that gives us O minus gas. That's the first electron affinity. The second electron affinity would be this one, plus an electron. This is the second electron affinity. We hadn't talked about that one yet. When we introduced the topic of electron affinity, we were only talking about neutral atoms. But we can have a first and a second. Okay. So is this going to be favorable? Well, the electronegativity of oxygen is pretty high. So it's going to attract that electron reasonably well. We could say this one is favorable. Is that one of our choices? Favorable, exothermic. So delta H is going to be negative. Now, once you've got this negative, right? You've got a negative source against a negative source, they're going to be repulsive, right? So you're not, this is going to be unfavorable. Favorable. And that means delta H is going to be positive. Okay, so that would be unfavorable, favorable. Oh, I see. This is exothermic. This is endothermic. All right, so that's another condition in there. Unfavorable favorable is first, exothermic. Unfavorable is second, endothermic. Yeah, so D would be the answer. Now, I don't know if you're wondering, but we've already said that when oxygen forms an ionic compound with something, it tends to go 2- because it wants to complete its octet, right? Add one, you get here, add another one, you get to there. Well, we're saying that the first one is favorable, and the second one's unfavorable. So how do we get to our octet if this one's unfavorable? It's a summation of the two. This one is exceedingly favorable. Much, much more favorable than this one is unfavorable. So when you put them together, overall, the formation of the 2- ion is favorable. That's the only way I can reason it. All right. 27. We're actually going to do a calculation. Using the following reaction data, calculate the energy of an HF bond. Oh. Okay. Hmm. The energy of an HF bond. Let's look at it this way. HF gas is going to be H plus a gas plus F minus gas. Okay. Okay. So I think we're in Hess law territory here. This would be the energy of the bond. You have to put energy in to do that. So this would be our target. That's our target right there. Okay, what do we got going for us? HF gas, we got the second one, which needs to be reversed. Right? We've got 2 HF gas yields what? H2 gas and F2 gas. H2 gas plus F2 gas. And now the delta H for this one is going to be a positive 542 because we flipped it. But we only need one of these. Right? So we have to go 1/2. And so now we got HF gas yields 1/2 H2 gas plus 1/2 F2 gas. And that makes this one 271, right? Kilojoules. Yeah, that's right. So we're going to use this one right here to take care of the HF side. Now we need to do the H plus and the F minus. Actually, that's not right. We're not forming ions here. Those are free atoms. Yeah, they're free atoms. Okay, so the next one we have we need H on the right hand side and H2 on the left hand side, and that'll do fine because H2 is on this side, we want H2 on this side. So H2 gas for that one yields 2H gas. And that value is 432. Right? But we only need one of these, right? One of those. This is our target. We only need one of those, so we need to do 1/2 of this one also. Should have put this over here. Put 1/2 of that one. So now we have 1/2 H2 gas yields. 1/2 of this one is H. Right? And half of that is, let's see, 1, no, 6, 1, 2. Well, carry the 1, yeah. Okay, so now we're going to use this one. And then we do the same thing for the fluorine, right? We have a fluorine in there like that. Yeah, just like that. Okay, so now we got the fluorine yields 2F gas, and that value, let's see, we're still using this one. We're using this one. And that's 154. But we need 1/2 of that one also. Right, because we only need one fluorine for that. So if we do 1/2 of that, we get 1/2 F2 equals the single F gas, and then 1/2 of this value, which is 77. correct? Nope. Yeah. No, that's not right. 7, 7 is 14 plus 1. Yeah, that here. Okay. So we're using this one and this value. So now that we've got, let's see if we've added up correctly. All right. We got an HF here, right? That's good. That's good. We got an H here. That's good. We got an F here. That's good. Now, when we combine this one with this one, 1/2 H2. That's gone. 1/2 F2. That's gone. Right, we use this one, this one. Okay, we're good. So now we just need to add those values together. Y'all remember Hess's law, don't you? Fondly, I hope. 564. 564 kilojoules should be the energy of an HF bond. Okay. We got time for one more, I think. Just when you thought you could forget about Hess, comes back to bite you. #28. All right. As indicated by Lewis structures, which of the following would probably not exist as a stable molecule? Okay. A, B, C, D, and E. All right, what do we have to choose from? CH3OH? Huh? CH2O? CH3O? C2H2 and C3H4. Okay. Based on our Lewis structures. All right, what do we got here? We got 4 plus 4 is 8 and 6 is 14. 14 electrons. Here we have 4 plus 6 is 10 plus 2 is 12 electrons. Here we have, let's see, 3 plus 4 is 7. Yeah, 7 plus 6 is 13 electrons. Here we have 2 times 4 is 8 and 2 is 10. And here we have 3 times 4 is 12 plus 4 is 16. Valence electrons. Now we can draw structures. Now this one's going to have carbon and hydrogens like that. We can tell that because of the way it's written. This gives us a partial structure. This is going to have an oxygen here and then another hydrogen there. So 2, 4, 6, 8, 10. So now we have 4 left over. Where do they go? Can't go on the hydrogens. Hydrogens all used up. So we have to put the 4 here, like that, like that. That gives us an octet. Duet, 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 duet. Octet. 2, 4, 6, 8, octet. That's good. That's fine. How about this one? Carbon in the middle, oxygen, and then 2 hydrogens. Okay, so that's 2, 4, 6. That means we have 6 left over. 2, 4, 6. Okay, used up all our electrons. And we need to make an octet here. So let's pull these 2 over like that. That works. In fact, that's formaldehyde. How about this one? Did I count them right? 4, 7, 6, 13. That's right. Okay, if we do this one, that, like that, like that, and then oxygen, we got 2, 4, 6, 8. 6, 8. That means 5 electrons left over. 2, 4, 5. 2, 4, 6. That's not very good. How about formal charges? Formal charge on carbon, right? It starts off with 4, and it's got 1, 2, 3, 4, right? So its formal charge is 0. This one, oxygen starts off at 6 valence electrons. 5, 6. Well, that's 0. I guess it could be. The problem is that free radical, which is not entirely impossible. 2, 4, 6, 7. It would be deficient. Right? And that's why it says probably not exist. So this one is questionable. This is carbon, excuse me. 1 hydrogen here, 1 hydrogen there. 2, 4, 6. So we have 4 electrons left over. 1, 2, 3, 4. So we need to make 2, 4, 6. Let's move over like this, like that, make a bond. Right? 2, 4, 6, 8, 10. Still got 10 electrons. That's good. But we still don't have an octet here. What if we move these two together and make another bond? Yeah, that'll do it. 2, 4, 6, 8, 10. That's acetylene. That one's good. That one's good, good. And C3H4. C. H. C3H4, okay. 2, 4, 6, 8, and 12. All right, so 12, we've got 4 electrons left over. So we move from the outside in. Okay. We can put 2 more here and 2 more here. That 2, 4, 6, 8, 10, 12, 14, 16. Okay, got all our electrons in there. Now we have to make an octet. So let's move these over here and make an octet. Right. That's good. Now, how about these two over here? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. That's good. Yeah, that one works. So this is the most likely one. That's the problem child right there. All right, how we doing? We're good till 45. Gonna do the next one in 3 minutes. Using the following electronegativity values, select from the following fits the given statement. The molecule containing a carbon atom with trigonal planar geometry. We might be able to do this one. That'll give us a little more extra time on next Tuesday. If I can get this one done. If we got, and this is none. Okay, so we have CH3, CHO, CO2, CH3Cl, C2H6. And we want carbon atom with trigonal planar. Right? Trigonal planar geometry has nothing to do with electronegativities, right? You can do that without the electronegativity. So that's useless information. Right, we know this one is linear. Right, we've drawn that one before, so that's not it. This one is going to be tetrahedral. Right? Carbon, like that, like that, like that, like that. Let's see. 4 and 3 is 7. 7 is 14. 2, 4, 6, 8. Minus 8. That means we've got 6 electrons left. 2, 4, 6. There you go. That's tetrahedral. Okay, how about this one? Or let's go up to this one. This is 2 times 4 is 8, and 4 and 6. So it's 18 electrons. We got our hydrogens here. This is the way we write organic molecules. I've told you this before, but I'll tell you again. When the hydrogens are to the right of the carbon, that means they're attached to the carbon, not that carbon. Right? It's not a bridge. Right. So this carbon is attached to that carbon. That means we got a carbon here. Then we have a hydrogen here, and we have an oxygen there. So that's 2, 4, 6, 8, 10, 12. We have 6 electrons left over. All right, we start from the outside in, 2, 4, 6. Excuse me. This has already got an octet. We need an octet here. So do that. This carbon has 1, 2, 3. This is trigonal planar. Yeah, this one's tetrahedral. 1, 2, 3, 4. This one's 3, trigonal planar. How about this one? Let's see. That's 2 times 4 is 8, plus 6 is 14. So we have a carbon attached to a carbon. Then we have 1, 2, 3, 4, 5, 6 hydrogens. 2, 4, 6, 8, 10, 12, 14. Use them all up. 4 around that one, 4 around this one. This is tetrahedral. Right. So this is the only one that's got a trigonal planar in it. Right. A. Okay. That's good. We'll pick it up with 34. Let me mark that in here.